Hello, my dear mathematicians. Welcome to this wonderful discussion. We'll be tackling a very rare type of integration, that is partial integration. And this is a method we use to solve some kind of simple partial differential equations. Now, we have to remember that integration is the reverse of differentiation. This should stick at the back of our mind while we are dealing with this kind of integration tonight. So the examples that we are going to tackle include this, that. Then this kind is provided with boundary conditions so that you are able to eliminate some constants. So keep tuned in and we see how we solve these problems. So in this problem, we have del u, del t is equal to 5 cosine x sine t. So while dealing with such a problem, and remember we are differentiating, this is a partial derivative of u with respect to t. So if we want to solve here, we shall be able to integrate this with respect to t. So if we integrate this with respect to t, remember this is going to give us u, which is a function of x and t, meaning t is going to be the variable here, whereas x and 5, the 5 cosine x term is going to be a constant. So even if I wanted, I can say 5 cos x, let that 5 cos x equal to, for example, c, so that I have del u, del t equal to c, then sine of t. Now I'm going to be partially integrating this for us to get the solution. So u will equal to integrating del u, del t with respect to t, giving us integrating c sine t with respect to t. And what does this give us? This gives us c. If we integrate a sine, we get a negative cos of t, then plus a constant of integration. So the constant of integration here is going to be k. Let us assume that it is k. Therefore, u equivalent to, so u is equal to, we said c is equal to 5 cos x, and we are multiplying it by cosine of t plus k becomes the solution. Let's look at another problem. If we have del u, del y, equivalent to this, y exponential x squared plus y squared minus x out of y plus 3yx. This gives you u, which is a function of x and y. So now that means for us to get u here, because if we have the first partial derivative, we shall just do partial integration once. So it will give us u, which will be integrating del u, del y with respect to y will equal to integrating y exponential of x squared plus y squared, then minus x out of y plus 3yx, and we are integrating with respect to y. So to minimize the complexity of this, I'm going to say let us say v is equal to x squared plus y squared, so that dv, okay, is equal to, we are going to, since here we are integrating with respect to y, we are going to differentiate this with respect to y. So this x, if we differentiate this with respect to y, this x squared becomes, so this becomes 0 plus 2y dy. What does that become? It means that dy will be dv divided by 2y. So let's integrate this, meaning integrating y exponential of x squared plus y squared itself with respect to y is equal to integrating y exponential of v, okay, times dy. What is dy? dy is dv divided by 2y. So this becomes, this and that goes, and we'll have 1 out of 2 exponential of v, obviously plus a constant, okay, which we shall keep somewhere that we will add on together when we finish the whole integration. So meaning, the moment we have minimized that complexity, it tells us that u, which is the integral of this, will equal to 1 out of 2 exponential of x squared plus y squared. Because after integrating this with respect to y, that's what we get. So let's integrate this with respect to y. We shall have minus x natural logarithm of y. We integrate this with respect to y again, we'll have plus 3y squared x everything out of 2. So the constant becomes f of x. This is an arbitrary function, f of x, that represents the constant of partial integration here. And so, what does this mean? It means if I partially differentiate this function, okay, this u, with respect to y, still this would go back to 0, okay? But how can I determine this f of x? Usually, I determine it if I'm given the boundary condition. So for that matter, if we have f of xy equivalent to, for example, del f, okay, del, for example, and I'm integrating, okay, if I integrate this del f, del x with respect to x, this should give us, since it is a function of x and y, this is going to give us, maybe, let me say this becomes the integral, the capital F, x, y. Then we shall add a function of y. Yes, if we were integrating del f, del y with respect to y, for example, this becomes, let me say this is f1, then this becomes xy, okay, plus now a function of what? A function of x. So this f of y represents the constant of integration, but it obviously is a function of y. And why do we call it a function of y? Because we know this general function is going to be a function of x and y. And that constant, even if we differentiated the whole of this with respect to x, this would go to 0. If we differentiated this with respect to y, we would get back the del f del y, and this would go to 0. Solve the differential equation, del 2, del u, del x, del y is equal to 6x squared cos 2y. So here, we said that integration is the reverse process of differentiation. So if we had u, okay, the first derivative of u with respect to x was del u, del x. And then the next one, they differentiated this with respect to y. So we had del 2 u, del x, del y. So meaning, what did we differentiate with respect to last? It was with respect to y. Meaning here, when I'm doing integration, it's going to be the reverse. I'm going to integrate with respect to y first. So this is going to be, first of all, I will have del u, del x, which will equal to integrating del 2u, del x, del y with respect to y. This is equal to integrating 6x squared cos 2y, okay, with respect to y. And this becomes 6x squared. And this is a, when we integrate a cos, we get a sine, 2y, and divided by 2. Then we shall add a constant there. So del u, del x becomes 6x squared out of 2 sine 2y plus a what? A function, okay? A function of x. Because since we integrated with respect to y, that means this constant is going to bear a component that is of x, not of y. So we partially integrate this again, and u will be integrating del u, del x with respect to x, which will equal to integrating this now will be 3x squared sine 2y plus f of x with respect to x. So what does that mean? U is going to be 3x cubed out of 3 sine 2y, because we are integrating with respect to x. This sine 2y becomes a constant, and then plus x, f of x. Since we are integrating with respect to x, we shall have a constant of integration that has a component of y. So we shall add f of y. And that becomes the solution to our problem. But to make it better, we can cancel this 3 and we'll have x cubed sine 2y plus x f of x plus f of y. Next problem, we are solving del 2u, del x2 is equal to 6x squared 2y minus 1, and we are given the boundary conditions that x is equal to 0, then del u del x, or the first partial derivative of u with respect to x, is equal to sine 2y, and u is equal to cos y. So what do? We are going to have del u del x. Okay, let's first integrate it with respect to x. Okay, this is only having x, so we shall assume that when they differentiated this before, okay, at first they differentiated with respect to x, and again they differentiated with respect to x. So that's what it means. So that would mean that we shall be integrating 6x squared 2y minus 1 with respect to x. So this becomes del u del x, and this is going to be 6x cubed divided by 3 into 2y minus 1. Since we are integrating with respect to x, we shall have a y somewhere. So we shall have f of y as part of the constant of integration. So now we are told that del u is equal to sine 2y when x is equal to 0. So I'm going to substitute in here so that I have del u del x, which is sine 2y, will equal to, this is 2, x is 0, so cubed into y, 2y minus 1, plus f of y. So this boundary condition is helping us to determine the function f of y. And this is going to be, this is 0, so f of y is equal to sine 2y. So meaning that del u del x will equal to 2x cubed into 2y minus 1 plus f of y, which f of y is sine 2x, is sine 2y. So now u will be integrating del u del x with respect to x, and this becomes integrating 2x cubed 2y minus 1 plus sine 2y with respect to x. So u will equal to 2x power 4 divided by 4 into 2y minus 1. Now, this is with respect to x, so plus x sine 2y plus another function that is having a y component. So we are calling it capital F of y. So again, we apply the boundary conditions. What do they say? That when x is equal to 0, u is equal to cos y. So x is equal to 0 and u is cos y. So we put in those conditions, and this is going to be cos y will equal to, this is going to be 0, because 0 to power 4 into 2y minus 1. Obviously, this is 2 out of 4, okay, plus 0 times sine 2y plus f of y. So all of these go to 0. This is 0, and that is 0. What is cos y? So f of y will equal to cos y. So if f of y is equal to cos y, meaning that u finally shall become, now substituting on all these other components that we have, this will be x to power 4 out of 2 into 2y minus 1. then plus x sine 2y plus cos y. So that becomes the solution to this problem. Next, we are given that del 2u del x del y is equal to a cosine of x plus y, given that the first partial derivative of u with respect to x is equal to 2 and y is equal to 0, then u is equal to y squared when x is equal to 0. Now, here again we said integration, the reverse of differentiation. So what became the this function was differentiated with respect to y last. So we shall integrate it in reverse. In other words, we shall integrate this function with respect to y first. So meaning, when we integrate it, we'll have del u, del x, and this is equal to integrating del 2u, del x, del y with respect to y. So this becomes integrating cos x plus y with respect to y. And what does this become? This becomes sine x plus y, then plus a constant of integration, which is going to be in terms of x. So f of x. So del u, del x is equal to sine of x plus y plus f of x, an arbitrary function, as we said, but which is in terms of x. So next we are integrating this to get u. So u is equal to integrating del u, del x with respect to x, and this will be integrating sine of x plus y plus f of x. So we are integrating this with respect to x. So if we integrate that, this becomes u, which shall equal to, this becomes minus cos x plus y, then plus x f of x, and now plus f of y, because if we integrate here and we are doing partial integration, so if we integrate with respect to x, then we shall have a constant of integration, which is a function, an arbitrary function f of y. So apply the boundary conditions. The boundary conditions that we have is that del, okay, so let's first, now here, let's apply the boundary conditions. So when we apply the boundary conditions, what does this become? We are told that del u, del x is equal to 2 when y is equal to 0. So when y is equal to 0, del u, del x is equal to 2. So we substitute in here. So this becomes 2 is equal to, when we put y is equal to 0, this becomes sine x, then plus f of x. So meaning f of x becomes 2 minus sine x. So we put back this condition that f of x is equal to 2 minus sine x, meaning del u, del x becomes sine of x plus y, then plus 2 minus sine x. Now to get u, we integrate partially this with respect to x. So this becomes integrating del u, del x with respect to x, equivalent to integrating sine of x plus y plus 2 minus sine x with respect to x. What does this become? I will have u equivalent to cos of course minus. Integrating a sine, you get a negative cos. So with respect to x, this is just 1x. So it remains cos x plus y. Y is a constant and therefore we don't mind. Plus 2x minus. If we integrate a sine here, we also get a minus cos. And then this negative will die and we shall have cos x. Then plus a constant of integration, which is going to be an arbitrary function in terms of y. So we apply the boundary conditions to find f of y. So we are told that u is equal to y squared when x is equal to 0. So when x is equal to 0, u is equal to y squared. So we substitute in here. Y squared will equal to, this becomes minus cos y Yes, because x is 0. Then plus 0 plus cos 0 is 1. Then plus f of y. So f of y becomes equal to what? This becomes y squared plus cos y minus 1. So meaning we shall have u equivalent to, we just substitute in all that we have. So this becomes minus x plus y plus 2x plus cosine of x, then plus y squared plus cos y minus 1. Finally, u becomes, just rearranging this, I would give you cosine x minus x plus y, then plus 2x minus 1 plus y squared. Then obviously we'll have plus cos y. So remember to subscribe, remember to comment, and enable us to serve you better. Thank you.